as promised, this theorem, Theorem 32, the projection recovery theorem, is going to be so important that I want to make sure we don't go away for spring break before we have one more conversation about this. And so what this theorem says is that if I have an orthonormal basis for Rn, in other words, if I have enough vectors that are orthogonal to one another and which span the entirety of my vector space, Rn, then when I project any vector onto each of those basis vectors, and I add up those projections, that I get my original vector back. I get my original x back by adding together the sum of all of its projections onto the VIs. So the reason that this is, well, let's do a quick plausibility check. Here's just an example where it's sort of sketched as though it's in R2. In the example on the left, I've got a couple of vectors v1 and v2, which I've sketched in such a way as to suggest that they are not orthonormal. They're not orthogonal one to another, and they don't have unit length. If I project this point that I've drawn here in orange, let's call it B, no, let's call it x, because we're trying to keep with the notation that we have above. If I project x onto v1, let's take a look at what we get here. So projecting x onto v1 is going to be a matter of kind of dropping a perpendicular and placing the point right here, which is the projection of x onto v1. So let's call this x1, just for the sake of calling it something. Then likewise, I need to project that onto v2, which if I extend my vector v2 and then drop a perpendicular to it, try and give us a diagram where we can believe our eyes here. So let's call that x2. So there are the two projections. And if I then add x1 plus x2, by the way, if when you add a couple of vectors in the picture, where does their sum go? How does this? Say again?
To the vector.
Okay, so it would be like saying, if I want to do x1 plus x2, I can start at x1 and from there proceed along the x2 direction, right? So I'll just take another copy of that vector and kind of sketch it in over here. And so here's x1 plus x2, somewhere out here. Sometimes it's called the parallelogram law for adding together vectors, right? The sum of two vectors lies at the opposite vertex of a parallelogram, where the two sides of that parallelogram were spanned by the vectors in the first place. So what we notice is that in this example, x1 plus x2 is very much different from x. Right? X is not equal to the sum of its two projections onto v1 and v2. Whereas if we try it in the example on the right, so I'll drop a perpendicular from this x down onto v1, call that x1, and I'll drop a perpendicular from x onto v2 to find the projection of x onto v2. And try to be accurate here again. Here's x2. And if I then add x1 plus x2 together, I end up getting exactly back to my original x. Okay. So that's the difference in situation. On the basis v1, v2 over here on the left was not an orthonormal basis. Not orthonormal. And so x was not equal to the sum of its projections. Sum of projections. But in the example on the right, we did have a basis which was orthonormal. And so x was equal to the sum of the projections. So I think we could have even been stronger in the statement of this theorem and said if and only if. But we don't really need both directions of that to do what we're going to do. So that's the flavor of this theorem. And we hadn't, as of the end of the video in which the cliffhanger appears, figured out how to prove this thing. Why is orthonormality important for recovering x as the sum of its projections? So Greg's question just now was, why was it important that the vectors v1 and v2 be orthonormal? Is it enough that they be orthogonal and not necessarily normalized? And as far as the pictures that are drawn up here are concerned, it doesn't matter. Right? Somehow it's just the angle and not the lengths of these vectors which are making it work the way that it works, which would make sense if all that we cared about was the projections, right? Because the projections are going to only depend, the projections onto v1 and v2 do not depend on the lengths of v1 and v2. So where the orthonormality part comes in is actually in the formula that's given to us in the theorem. Because if you look at this, the way that the theorem is set up, let's take a look at this first term right here, v1 transpose x. That is the projection. This is the projection of x onto v1, but only if v1 has length 1. So if and only if v1 transpose v1 is equal to 1. So the orthogonality is really what makes the difference between being able to recover x as the sum of its projections or not. It's the normality, in addition to the orthogonality, that gives us this formula that's written in the theorem. So the orthogonality is probably really what powers the proof when we do the proof. But if we're going to use the formula that's given to us, then we're also going to need the normality. Pat?
Now, when it's orthonormal, will it always make a rectangle or a square?
If by rectangle or square you mean a quadrilateral with right angles, then yes. Because right angle is exactly what we mean by orthogonal. And probably square is a better way to put it, because in that case, all of the vectors on the edges of your polyhedron will have the same length, which would be the case for an orthonormal set because they all have length 1.
So in this case, it is a rectangle, or is it a square?
In this case, these two vectors, the purple vector and the green vector, would form the sides of a square. The projections of x onto those vectors may have different lengths, one from another. But the angles at the vertices of that quadrilaterals are still guaranteed to be right angles. But they might form a rectangle in general, because we can't expect the projections of x onto the vectors to have the same length. But if we have an orthonormal set, we can expect the vectors themselves to have the same length.
So it's if and not.
Namely 1. So where we had left this proof is in the equation that's given to us here, x equals v1 transpose x plus v2 transpose x, and so forth. We argued our way into that being the same as the result of multiplying a matrix whose columns are the v1s up through the vn's, multiplied by a matrix whose rows are the v1s up through the vn's, multiplied by x. And so we have to justify why this should be a true statement in the situation where v1 up through vn forms an orthonormal basis for Rn. So why should we expect that this is the case? So to substantiate this, tell me something about the matrices that we see here, v1 up through vn. Let's say we call that matrix on the left here, let's call that M. So that what we're looking at here is M times M transpose times X. What do we know about the matrix M based on the fact that v1 up through vn is an orthonormal basis for Rn? What can we say about it? It's an n by n matrix, so it's square for sure, definitely. Okay, that's promising. Ah, invertible. Why? Right, so not every square matrix is invertible, but somehow its orthonormal columns are playing a role here. What can we say about it?
No, I just disagree with the n by n. If we're assuming n is the number of v's, not the number of vectors, it's the number of entries in each vector.
Number of entries in each vector. On the other hand, each of these vectors, yeah, so Heather's cluing in on this right here. It's an orthonormal basis for Rn. That means that each of these vectors belongs to Rn. And so in addition to n being the number of vectors, it's also the number of entries in each vector.
Yeah.
Right, so it's both and in this case. And I want to go back to this invertible assertion. How do we know this matrix is invertible?
The columns are going to be independent
Yes. Why?
because of the definition of orthonormal.
Okay. So that's actually not quite by definition. There's a theorem, and I think the theorem appears earlier on this sheet. The columns are linearly independent since they are orthonormal. And any orthonormal set is linearly independent by a theorem, not by definition. So we would have to convince ourselves that that's true. But we can take that result because it's an earlier result from this sheet. So because the columns are orthonormal, they are in particular linearly independent. And if the columns are linearly independent, that means that this matrix is invertible. Great. Okay, so far that's what we know. That's our evidence about the matrix M. Now what about M transpose? If the columns of M are orthonormal, then what do we get when we multiply M by M transpose? What kind of a matrix? Well, so we'd like to get there, right? Ultimately, where we want to get to is we want to get to argue that M times M transpose is the identity matrix. But we need to know why that is. So what is M transpose doing?
Canceling.
We'd like to argue that it is canceling, but we need to know why. So let me ask this question to hopefully try to lead us there. The whole point of Math Material Monday 3 was that if we choose an orthonormal basis for a subspace, then it's very easy to write down a projection matrix onto that subspace. So this is the throwback here. So if A is a matrix whose columns are an orthonormal basis for a subspace S, then what is AAT? It's a formula for the projection matrix onto S. So that was kind of my selling point for why orthonormal sets are a good thing in Math Material Monday 3. Is because if we have an orthonormal basis for a subspace, then we don't have to invert any matrix, because typically the projection formula is, what is it? A times A transpose A quantity inverse times A transpose, right? That's the typical formula for a projection matrix if the columns of A are not orthonormal. But if the columns of A are orthonormal, then this whole inverse of A transpose A in the middle just drops out, and we're left with A times A transpose. So M transpose is therefore a projection matrix. It's a projection matrix onto the vector space spanned by V1 up through Vn, because the V1 up through Vn's are orthonormal. But if M is invertible, then what do we know about M transpose? That M transpose will also be invertible. There's a nice formula in linear algebra that says that the inverse of the transpose is just the transpose of the inverse. So if one matrix is invertible, then its transpose will also be invertible, and its inverse is given by that formula. So that means that M times M transpose will also be invertible, because the product of two invertible matrices is always invertible. So what we have is an invertible projection matrix. What do we know about invertible projection matrices? Yeah, exactly. That was a result from homework number 1. So the fact that this matrix is invertible and that it is a projection matrix, and the key algebraic property of a projection matrix that we could use for this, by the way, and let me ask you this, because I don't think we've framed it this way before. If I have a projection matrix, what do I get when I square it? If I do a projection twice, I project onto a subspace, and then I project that thing onto the subspace again. It's the same thing as projecting once, right? Projecting and then projecting again. You don't do anything new the second time. It's like the old Seinfeld routine about putting clothes into a dryer, right? You can't over-dry something. Once something is dry, it's dry. So once something is projected onto a subspace, it's projected. You can project it again, but it's not going anywhere. You can't over-dye, you can't over-dry, and you can't over-project either. P squared is equal to P for that reason. But if P is also invertible, then what can I do in this equation? Just multiply by P inverse. P inverse, P inverse. And on the left-hand side, P inverse is going to cancel one of those P's. And on the right-hand side, P inverse P is identity. So this is an algebraic fact, really, that in algebra, if something is equal to its own square, it's called idempotent, by the way, but if that thing is invertible, then it must be itself the identity. And so what we've proven, therefore, is that MM transpose is equal to the identity matrix. And because MM transpose is equal to the identity matrix, we've proven this equality. Because then this whole thing in the middle just drops out and becomes the identity. So that's the projection recovery theorem. It tells us that if I take the sum of the projections onto all of the elements of an orthonormal basis, then what I will get back is my original element. Philosophically, why we like this, and this is something that hopefully will become apparent after the spring break and when we start to get into the more intricate examples of what this looks like, is that it's often much easier to understand the individual building block projections one at a time, and then have some reassurance that if I find each one of those individual building blocks and I add them all together, then I'm going to get my big picture back. So it's a means of recovering a complicated object as the sum of a bunch of hopefully simple little objects. And we can find each of those hopefully simple little objects through a process that looks pretty simple, a process of just projecting the complicated object onto a simple direction. It's a bit like kind of reconstructing something from all of its shadows. I know a shadow in the V1 direction is this. I know the shadow in the V2 direction is this. I know the shadow in the V3 direction is this. If those questions are all easy to answer, and we have a theorem like this one, then all we have to do is answer all the easy questions and add them together, and we get a complete picture from the sum of all of the shadows onto the various directions. So we've done it with kind of vectors, thinking of them as elements in Euclidean space here, but where we want to push to after spring break is to think about doing this with functions. Think about the case where x is some complicated function that we don't possibly understand, but all of its projections are something that's simple to understand. If we can get to that situation, then we can recover our complicated function as the sum of a bunch of less complicated functions. And if we have this theorem, then we know we're going to get the complete picture by doing that.